In this video, I wanted to go over how to find the net force on a charge. This problem asks us for the force on the electron right here, and there are two other charges right here. So the first step is to draw a picture and draw all of the forces acting specifically on this electron. It's going to feel a force from each of the other two charges. We have a charge over here, which is also negative, right? Negative 8e. That means that the magnitude of this charge is 8 multiplied by the charge of one electron, which is 1.6 times 10 to the negative 19. So you do have to multiply these numbers together. This is the charge that's here, but it's negative, which means that the electron is going to be repelled from this charge, so we draw a repelling force. You can draw a line connecting the two charges, and then you draw that force in the opposite direction. And then we have a positive charge over here, which has a magnitude of 9 times e, so 9 times 1.6 times 10 to the negative 19 coulombs. Make sure to multiply e, which is in coulombs, by 9. This charge is positive, which means that our electron over here is going to be attracted, because unlike charges attract. So now that we have visualized our two forces, let's go ahead and label them. I called this one F21, and I called this one F31. That means that I'm calling this charge number 1, number 2, and number 3. So we are given this angle theta right here, which is this angle right here. If we extend this line over here, this horizontal line, then we can see that these are alternate interior angles. So we know theta for this angle right here. The reason this is useful is because whenever we have a diagonal force, we need to find the components. So let's draw the components of F21. How do we get from here to here? We have to go to the right and then straight down. So those are our components. So the horizontal one is F21x, and the vertical one is F21y. F31 is all horizontal, so we don't have to worry about finding any components. We only find components of diagonal vectors. As far as the distances that we are given that the distance A, which is the distance right here, between the 9e charge and our electron. A is 5 times 10 to the negative 6 meters. The problem also gives us the distance over here, which is 3 times 10 to the negative 6 meters. We actually don't care about this distance over here because we're not asked about the force between charges 2 and 3. That's the only reason that we would need this distance. We only need the distances between the electron and the other charges. So from here, it's a vector addition problem. We have two forces acting on the electron, and we want to find the next force, the net force. I like to separate the x and the y directions, find the x and y components of both of these forces. So I automatically, without even thinking, I just write down for each force, I write down the x and the y component. So F21x, F31x, and then same thing for the y component, F21y and F31y. And then I fill in what I know. F21x is right here. It's the components that is adjacent to the angle. Adjacent always uses cosine. So it's going to be F21 times cosine of our given angle, which was 50 degrees. I've already put all these numbers in the calculator. Actually, let's back up a second. We forgot to solve for F21 and F31. Let's do that on the side. we should do that before we find the x and y components. So F21 is the force between the 8e charge over here and the electron. So Coulomb's law tells us that the force between the two charges is the Coulomb's constant times the magnitude of both charges. So we need to put Q2 in here and Q1 in here. Just a magnitude, you can put absolute value signs if you want to, just to remind you that this equation will just give you the amount of the force. And then you need to divide by the distance squared between the two charges. So let's call this R12, and we're going to want to do R12 squared. So this was Q2 up here. Q1 is a charge of an electron, so Q1, if we are just looking at the absolute value of it, is just going to be 1.6 times 10 to the negative 19 coulombs. That's E. Right, and Q3, we already mentioned, was going to be 9 times 1.6 times 10 to the negative 19 coulombs. Okay, so now we know everything that to plug in here. K is Coulomb's constant. K is 8.99 times 10 to the 9. So we plug in K, we plug in Q2, which is right here, plug in all those numbers, multiply by all these numbers, and then divide by this number, 3 times 10 to the negative 6, which you must square. Once you do that, you're going to get approximately 2.05 times 10 to the negative 16. It's better to keep as many decimal places as possible when you are, until you get to your final answer. So let's just say 2.046. Let's do the same thing for F31. The only difference between F21 and F31 is that F31 is the force between charges number 3 and charges number 1. So that means that we have to put in charge 3 and charge 1 instead of charge 2 and charge 1. Again, we're just putting the magnitude of the charge. We don't care about the sign of the charge. So our 1,3 is this A right here. That's the distance between charges 1 and 3. Make sure to square that. You'll get for F31 8.285 times 10 to the negative 17. Of course, this is all in newtons. So as I mentioned, we don't care about the negative signs because we already know the direction of the forces. So, sorry I wasn't super organized. Now we know exactly what to plug in for F21x. F21, which is this number right here, multiplied by cosine of 50. That's going to give us 1.31 times 10 to the negative 16. And then the y component of F21 is going down, which means it's negative. It's opposite the angle, it's going to use sine. Plug in those numbers, and we're going to get negative 1.57 times 10 to the negative 16. Of course, all of these are in newtons. And now we're looking at F31. F31 was all horizontal, all in the x direction, going to the left, which is negative. So F31 was negative F31. It's the whole force with a negative in front of it to indicate that it's going to the left. So negative 8.29 times 10 to the negative 17. I round on the screen, but I'm not rounding in the calculator. And then F31y, well, if it's all horizontal, it does not have a y component, so that's 0. Once you have found all of the components, we are now ready to add them. By adding the two x components, you're finding the x components of the resultant force, of the net force. When I add these two numbers, I get 4.86 times 10 to the negative 17. And over here, we just get that number for F21y when we add up the y components. Negative 1.57 times 10 to the negative 16. The next step, and we're almost done, since we know the x and y components of our net force, we go ahead and draw them. So the x component is positive, so I'm going to draw a vector to the right that's positive. That's fx. I don't have to draw it to scale, just indicating the direction. The y component is negative, so I'm going to draw that tip to tail, starting from the tip of fx, that's fy. Not to scale, but I just indicated the direction, made it go down. This shows us that F must be going this way. The net force on the electron must be going down and to the right, since the components are to the right and down. So we can go ahead and find F using the Pythagorean theorem, since we have a right triangle here. F equals the square root of fx squared plus fy squared. We plug in the numbers we just found for fx and fy, and that gave me 1.64 times 10 to the negative 16 newtons. That's the net force on the electron. Now we need to find its direction. We're going to find theta over here. So if we draw this theta, we know that the y component is opposite and the x component is adjacent. So that means that we can use the inverse tan of the y component, fy, divided by fx. This is because the tangent of the angle is fy over fx. So the inverse tan will give us theta by itself. When I do this, I like to keep the two components positive just so that the calculator gives me a positive answer. It's going to give me 72.8 degrees. Now that I have it visualized, I just need to give that angle the way that WebAssign wants. In this particular problem, although the problem states that it wants the counterclockwise angle, it actually doesn't. It actually wants the clockwise angle, and whenever you specify an angle as being clockwise, so going down from this positive x-axis here, that's going to be indicated with a negative angle. So that is the theta that we just found. So the final answer for the direction is going to be theta equals negative 72.8 degrees. And you can just write out the word degree in WebAssign, since there is no degree sign. If the problem had wanted the counterclockwise angle, if it had wanted this entire angle, then you would have had to do 360 degrees minus theta to get this big angle. But in this case, this is the final answer. Comment if you have any questions.